So, PostGIS is a 24-year-old project and has seen a lot of different ups and downs. But I think one thing that all 24-year-old projects have in common in some ways is the basket of exciting new features in any given year does not keep getting larger and larger. Now, one piece of software can only do so much, and the balance of maintaining what is there versus adding to what is there is not one that can infinitely add. And so in some ways the result is a view that development is asymptotically approaching some finite total of features, beyond which there is no point in adding any more. This is the idea that we're just getting close to perfection. The projects can just be done. Another way of interpreting this pattern is that the sum total of code to maintain just keeps growing, so at some point all effort becomes maintenance effort. And so I don't really want to talk in detail about every little tweak that happened in the last calendar year, because a lot of it is just effort in bug fixing and so on. The interesting stuff is the stuff that has happened over a longer time frame, over the last 5 years or so, that people maybe did not notice. That's what I want to talk about. And those things I want to talk about, which I consider PostGIS features, are not necessarily 100% in PostGIS, strictly speaking. The things that we call PostGIS, that thing is actually a mixture of native code that lives in the PostGIS source repository and of libraries that provide additional functionality. The GEOS computational geometry library, the GDAL raster library, the Proj coordinate reprojection library, and the Siegel computational geometry library for a start. So, surprisingly, some of the biggest features of the past years, they don't start out in PostGIS or even in GEOS. They are prototyped and tested initially in the JTS project, in Java. Java is memory managed, which takes away some of the development complexity. Once a feature is done, it is ported to GEOS in the C++ language. And then finally, the PostGIS code is updated to add SQL functions that call the appropriate GEOS functions. Smaller changes tend to be built in the most convenient or performance-specific places. For example, a lot of C++ related performance and code cleanliness changes have happened over the last 5 years. GEOS was originally ported from JTS in 2001. That is unbelievably prehistoric in C++ language terms. So just things like using the latest C++ standards, improving use of memory, getting away from manual memory management, these have all gone into GEOS, but are improvements that PostGIS gets leverage from because PostGIS uses GEOS. Finally, there's some features and improvements that are just completely local to PostGIS. Anything that involves indexing or caching or object access or having the fastest performance as an issue, that's best done directly in PostGIS. Calculations in GEOS involve first moving the geometry from the PostGIS memory space to the GEOS memory space. For small calculations, the overhead of the move can exceed the overhead of the calculation, so it makes more sense to do them in PostGIS. Things like reading a coordinate or reading a ring, calculating a length or an area, figuring out a distance, those are all implemented directly in PostGIS in C. Okay, so that's how the pieces of PostGIS come together and how we do development. What do we spend our time on? As I mentioned at the start, the balance of activity has shifted over the years. We fix broken things, which is kind of invisible. We improve the things we have, which is usually invisible. Sometimes a performance improvement will be big enough that people notice without measuring it, but that's kind of rare. And finally, we still do write net new things. But because we have a lot of code now, more time tends to go to maintenance, and that's sort of dull to talk about. We used to have more critical broken things, like bugs that could crash the database. Those used to be a lot more common. This is the number of tickets about things that crash the backend over the release history. It's almost stereotypical the system had the most crashers right around the 0.0 releases. We can also see that they've been going away over time. A lot of the broken things we've been addressing lately are cases that live at the boundaries of the system, that deal with very rare but legal questions, like what happens when an empty polygon and an empty point intersect? That's a live question. It's empty. Is it an empty point? Is it an empty polygon? If you said, who cares, you're on my side. But it's a question. It's a question you can ask the system, and we want our behavior to be consistent, or at least unsurprising. Similarly, there are a lot of algorithms that are quite unhappy if you feed them an infinite or a nan coordinate. But do you know how to create an infinite or NaN coordinate? It's quite hard, but it is possible. So it's a problem that can be exercised, but not one that people actually run into day to day. And it's not something that we can just disallow globally. PostGIS has historically been very tolerant of garbage input because if you can't read garbage, you can't clean it. So we've ended up gating a subset of functions with NaN and int filters. It's an ugly solution, and it can be improved further. Without getting too deep into it, because I can do whole talks about this, a lot of the improvements to existing features are things like performance. So the last 5 years saw many tweaks to GEOS implementations to do better things with memory, many moves to modern C++ tools like iterators and managed pointers. There are also some changes to PostGIS implementations for performance reasons. There, the big wins have mostly been in cleverly caching bits of data during common SQL operations, during joins mostly. Again, this is a deep and interesting topic, but the Coles Notes version is just, over the past 5 years, implementations of existing functionality have just gotten faster. But what I want to talk about is the new functionality that has arrived over the last few years. And it is embarrassing to say so, but of that new functionality itself, a lot of it is not new from a capabilities point of view, mostly, but from a performance and reliability point of view. But reliability and performance are what bring people to PostGIS to start with, so I think that these count. The first big update I want to focus on is the overlay NG work. Now, this is from about 2020. The overlay functions in PostGIS are actually backed by the GEOS library. The original GEOS overlay code dated from 2001. It was part of the initial development of JTS and GEOS. It was slow, but worse, it was not completely reliable. Like all overlay engines, it had to deal with cases where the pure math aspect, the infinite precision of geometry relationships, intersected with the finite math, the limited precision of actual computers. Without getting too deeply into it, calculating the intersection of two edges that are sufficiently nearly parallel can sometimes result in degenerate outputs. And the start of every overlay process is a noting step that finds all the places where vertices need to be introduced at crossings and near crossings. With the old engine, a degenerate result would eventually lead to a topology exception and processing would halt. So any overlay starts with a pair of objects, polygons in the most difficult cases. And you can see in this example that these rings cross in a couple places without nodes, and in a couple places have nodes that are close to the edges of the other ring. Noding is the first step in overlay, taking these notional mathematical points of intersection and actually calculating them in the computer. Overlay NG introduced two new noders, a snapping noder, which left most vertices untouched and snapped only nearby nodes, and then a snap rounding noder that conditioned to the entire geometry. Here's what the snapping noder would do before unioning our two polygons. Like, this picture is grossly exaggerated, but you can see that it has calculated the places where the rings crossed and snapped a node onto the tolerance grid for that crossing. But the other nodes that don't participate in an intersection, those nodes have been left alone. The snapping noder is fast, and it addresses a surprising number of the numerical precision problems, which in practice are generated by nearly identical segment endpoints, the kinds of nodes the snapping noder identifies and rounds onto the grid. Some cases still defeated the snapping noder, though. For those cases, the snap rounding noder is a big hammer that carefully rounds all the coordinates into a regular grid and identifies intersections in that grid space. This reduces the precision of all the inputs, but it results in 100% reliability. You can see how every single node of the input has been snapped into the underlying tolerance grid. The output shape is changed at every node, but the predictable input means the overlay routines are very reliable. But the best part is that the snapping noder is almost never called. It's slow, and it perturbs the whole input, but the snapping noder handles almost all cases perfectly. And here's where we get to some net new functionality. There was a less reliable overlay routine before overlay NG, but there was not a bulletproof precision reducer. Once you have a bulletproof snap rounder, you can do more things than just overlays. applying the snap rounder at lower precisions allows for precision reduction while retaining geometric validity. So in this case, we've got Europe. The reduced outline of Europe remains valid even under, as you can see, extreme conditions of rounding down to these 4 or 5 huge blocks. The second big change coming from JTS via GEOS is relate NG. Like overlay NG, relate NG is a big deal because it is a complete rewrite of a core piece of functionality. The most useful, in my opinion, the most useful spatial operation is the spatial join. And spatial joins are driven by spatial predicates. So reliable and fast predicates can make big differences to system performance. And the old implementations of Boolean predicates, that was correct, but they were inefficient for many cases. The new implementation, the relate NG implementation, aims to change that. So back to basics. All Boolean predicates are based on the dimensionally extended 9-intersection matrix, which you can see here. A complete characterization of the relationship between any two geometries. For this pair, the interiors interact one-dimensionally. You can see the II cell at the top left. The boundaries interact zero-dimensionally. See the BB cell in the center. The boundary of the polygon and the interior of the point interact zero-dimensionally. See the BI cell in the middle of the leftmost column, and so on and so on and so on. 9 different intersections. Being able to compute the full 9-wide matrix for any two geometries is a big deal. It is a much more difficult problem than just supporting a few Boolean predicates, which is why many spatial databases don't do it. The Boolean predicates are simple. They just take in two geometries and return true or false, depending on if the inputs meet a condition. And the condition is usually much more human-friendly to understand. Do the objects intersect? Do they touch? Do they cross? So the DE9IM matrix is a superset, the complete interaction model, while the predicates are a subset, a few common interaction types. The original JTS GEOS relate machinery was built knowing that the intersection matrix was a non-negotiable deliverable. Had to get done, so they got it done. And here's the thing, once you have a full matrix, you can figure out the value for any predicate just by reading the result off of the matrix. So the old predicates were built on top of a dirty little secret. And that secret was that no matter how simple the predicate was, and something like the intersects predicate, that's a very simple predicate. Under the covers, the system was computing the complete 3x3 matrix and then reading the predicate off of it. It's a very clever way to avoid code duplication, but it's also, for practical purposes, really, really slow. So the big innovation in relate NG is to build up to the full DE9IM calculation, but incrementally, with the context of the predicate being called. This allows the system to short-circuit a calculation as soon as the desired predicate is known. That's faster. Like for this example, a 10,000 entry multipoint versus a huge polygon, an intersects result pops out 600 times faster. That's because only one point needs to intersect for the predicate to be true. So the short circuit in this calculation is extremely effective. The old predicates were so slow that some special caching machinery was added to speed up repeated tests, which we called prepared geometry. A prepared geometry is like a SQL prepared statement in that it calculates some expensive information up front and then amortizes the overhead over multiple calls. The relate MG implementation retains that optimization and extends it to more of the predicates and even to the full DE9IM matrix calculation. So there is famously a four corners in the USA where Arizona, Colorado, New Mexico, and Utah meet. Did you know that Canada also has a four corners? It does, where the Northwest Territories, Saskatchewan, Manitoba, and Nunavut meet. Now, four corners locations have a pretty rare boundary condition in which only one point is shared between two polygons. Relate NG supports a prepared option for the full DE9IM calculation, in this case, evaluating the 4 million vertices in Canada to find the two shared corner cases in the set of provinces, Saskatchewan with Nunavut and Manitoba with the Northwest Territories. The whole thing now runs 25% faster than the old operation. Okay, so overlay NG, relate NG, that was a lot of net new code, but it was to carry out functionality that already existed mostly, just to do that work better. Now, the third new piece I want to talk about is a completely new thing, polygonal coverages. Coverages are a popular data structure in the GIS world. They are collections of polygons with shared boundaries that completely cover an area where any point in the area is only contained by one polygon. Polygonal coverages show up all the time in GIS. Parcels, states, counties, H3 hexagons, S2 cells, census tracts, those are all polygonal coverages. Coverages are great for the guarantee of a perfect coveraging. Every place with one polygon, no gaps, no double counting. They're also great because the knowledge that edges are perfectly shared allows us to merge polygons very fast and to simplify shared edges such that the simplified polygons are still a perfect coverage. But first, how do we get a perfect coverage? Anyone who has played with parcels, states, counties, land cover, they'll tell you most data is dirty, but there's a fix for that. The ST coverage invalid edges function is a window function. It looks at all the polygons in a set, and for each one of them outputs the places where it breaks topology, or null, where the polygon is in fact coverage clean. This zoning map of Vancouver is not coverage clean, and you can see all the places where it is not. But then what? Fix them all in QGIS manually? That's not practical for any non-trivial data collection. It's pretty clear we need a solution to that. And there is. It's like ST make valid, but it's for coverages. There's a coverage cleaner. ST coverage clean takes in broken data and applies some basic rules to make it valid. The algorithm identifies overlaps and gaps and repairs them if they are less than the gap maximum or snapping tolerance. Those tuning knobs are optional, and if you leave them out, the algorithm will analyze the inputs and determine some reasonable defaults. ST coverage clean is also a window function, so a cleaned or untouched clean polygon will be returned for every input polygon. Window functions are great for this work because it lets us match up the cleaned outputs to the original inputs, just replacing directly the new input with cleaned output geometry in one step. And now we have a clean polygonal coverage. What can we do with it? The reason this idea that a set of ordinary polygons that implicitly forms a coverage, the reason this is useful is because it is in fact very easy for the shared edges to be found and manipulated. A classic shared edge operation is a union, and the coverage union is that same operation but for clean coverage inputs. Because the system knows in advance that edges are perfectly shared, it can be very fast. Like here, unioning the 3,233 county boundaries in the US, a coverage union, which knows the inputs are clean, is 10 times faster than a standard union that has to build up an overlay from scratch. Sometimes unioning is a one and done operation, but for some mapping, it makes sense to be able to generate merged subsets very, very fast. A coverage of H3 hexagons, for example, where you want to union together a set of output polygons based on an attribute, or varying the threshold value of an attribute, or the same idea, but with a tiny shape like a census block. But the most popular use of coverage, I think, will be in polygonal simplification. When polygons are independent, not part of coverages, and you simplify them, the neighbors do not necessarily agree on where the simplified boundary edges should be. And the ST simplify routine is run one polygon at a time. So each one gets an independent simplification. Enter ST coverage simplify. This is also a window function. It takes in all the input polygons, and because they're a clean coverage, it can quickly find which edges are shared. Those edges each get simplified, and then the result is reconstructed in output so that each input polygon is matched with a simplified output polygon. This kind of data processing used to be done with external tools like MapShaper, but now it's built right into the core of PostGIS. And the best part, because all these new functions and all these new features are implemented in GEOS, these new big developments are not just being used by PostGIS. They're being used by other parts of the open source geospatial community. QGIS in particular is going to see a huge improvement using the GEOS coverage simplifier compared to the current code. Because the current code actually writes the data to disk, runs a copy of MapShaper using the V8 JavaScript runtime against the data, reads it all back in, all under the covers. The new GEOS code is native C++. It can be run directly inside QGIS. Okay, so I tend to be hard on raster in the database, but with the rise of raster in the cloud, I have slightly changed my tune. With the existing OutDB raster model and some new tools I added to allow cloud storage access keys to be used and Google logging to be exposed, you can access external raster collections from inside PostGIS. And that opens up access to a whole bunch of new data. Elevation grids, climate grids, real-time weather, like anything stored in raster grids can all be joined to vector on the fly without directly importing the raster pixels. GDAL has a dependency of PostGIS raster. It's been there since version 2. but we mostly used it for format reading and writing. We didn't take advantage of the fact that GEDOL has some cool raster algorithms. We didn't start doing that until the 3.2 release. Given a collection of discrete measurements, for example, it's possible to create a fully populated continuous value raster with the st-interpolate raster function. The interpolation algorithm can be one of several, including inverse weighted distance, which is what's being showed here on the slide. And while it's possible to read averages and sums off rasters, discrete value reading was limited to points until PostGIS 3.2. The setZ and the setM functions allow every vertex of a geometry to get a value read off an underlying raster. Now, this is useful for lines in particular, but any multi-vertex object can be populated using these functions. Maybe you're reading an underlying elevation or weather grid onto a projected path or onto a collection of objects like building centroids. Finally, given an input continuous raster, isolines can be generated. So for things like travel times or weather maps, temperature or pressure isolines, or just for the standard use case of generating contours against elevation. As always, I think the most compelling cases will be ones where the inputs are dynamic and changing, like deriving some kind of live input from the state of the database. Cloud use cases are becoming more and more common. So at the same time that I added Google algorithms, I updated the OutDB raster code to allow any configuration parameters, including access keys, to be set, and to expose the GEDOL logging information to the Postgres logging output to make it easier to debug connections when setting up remote raster access. GEDOL and GEOS are not the only libraries that have been progressing and adding features over the years. The Proj library was mostly defunct until a few years ago. Proj was picked up by members of the Danish geodetic team and modernized to more correctly handle datums and transformations. Things like vertical datum transforms and stuff like that. The model was enriched sufficiently to support arbitrary pipelines of transformations, and the updated st transform pipeline function in PostGIS exposes that new capability to end users. On to clustering. PostGIS has had clustering support for a long time. So long, in fact, that the first few clustering functions, cluster within and cluster intersecting, made a very poor interface decision. Their return value is a single huge geometry collection. So in order to figure out which geometries are in which cluster, the user has to actually dump the collection and analyze the components. That workflow, frankly, sucks. The correct user interface for clustering is to use a window function and to return the cluster number for every input geometry. That's what the dbScan clustering and k-means clustering functions do. And now the cluster within win and cluster intersecting win functions do too. Note that because we are crazy about backwards compatibility, the old signatures are still there with the same old awful behavior. But we do now have window versions, which are much nicer. We've also picked up some new functions from SQL, which are exposed in the PostGIS SQL extension. We have split that module off from the main module to make it easier for people to compile PostGIS without SQL if they want to. We also changed the naming convention so that overlapping functionality between GEOS and SQL would not result in SQL name collisions. From the visibility functions, the partitioning functions, you can form the idea that SQL is heavily influenced by problems that arise in computer graphics. The support for volumetric geometry in PostGIS is entirely dependent on the SQL library, and we picked up two new volumetric functions this release, a convex hull in 3-space and a union in 3-space. The tools for creating and exporting the volumetrics in PostGIS are still a little primitive, but with 3D visualization support in QGIS, it's becoming more and more useful with each passing year. The inevitable first question in this kind of talk is like, what are you going to do next? And let me preempt that question by saying predictions are hard, especially about the future. One thing that remains true is that if a customer shows up with a need, that need is going to go to the top of my list every time. Both because they're paying good money to be supported, but also because a customer problem is by definition a real world problem, and I really want to bias development effort in favor of spending my time on that kind of problem rather than figuring out what the intersection of two empty polygons should be. That said, there's a few options on my list of things that might be neat for PostGIS. The geography type has limited algorithm support right now, and there is an S2 library. It has implementations of those missing things, stuff like union and intersection on the sphere. So an S2 module like the SQL module, that might be worth attacking. It's a heavy dependency, so the packagers would hate it. There is still one algorithm left in Google that I haven't exposed yet, the viewshed feature. It has about 1 million different knobs to tune, but it's something that telecom users might be keen on. Or maybe not. It might be too coarse to be of interest compared to like high resolution models with buildings and trees and stuff. And finally, I've been toying with a polygon skeletonizer, but I'm kind of unsure about whether to continue with that work because my approach seems to have a lot of failure modes, and it really sucked to release it and then be buried in tickets saying, your thing is broken for this polygon and for this polygon and for this polygon. So that is what's new in PostGIS. Thanks very much for your time.